Hey guys, so we start with module 2 of API 510 pressure vessel inspector. In a nutshell, the pressure vessel inspector should know about ASME section 8, pressure vessel construction code, welding inspection and WPS, ASME section 9 and 577, non-destructive inspection examination, ASME section 5, damage mechanism and corrosion, API 571, positive material identification or material verification program, API 578, inspection of pressure relief valves, API 576, repair of pressure equipment, PCC2, this is the ASME document, and the all-important pressure vessel inspection code plus the associated API 572, pressure vessel inspection practice, and finally have sufficient general and safety knowledge. In API pressure vessel inspector examination, you have two sets of reference documents as a study material. One set are ASME, which are section 5, pressure vessel construction code, section 9, welding, and section 5, non-destructive testing. And the second set would be the API documents, such as 572, pressure vessel inspection practice, 576, PRD, 571, damage mechanism, 577, welding inspection, 78, PMI, PCC2 repair, and finally the all-important 510 pressure vessel inspection code. Most of the questions from these codes are normally in open book part of the examination and of calculation type. So you don't need to memorize them, but you should know where to look for when solving this open book question. And this is especially important because the search button is disabled during the exam. So you should know how to navigate through them. When reading a code, I would suggest that don't immediately go into that section. Look at the table of contents, look at the scope, the purpose of the code, what it covers, what it does not, and especially the vocabulary. So get the bigger picture, look at the list of tables, list of figures, see what the code is talking about or the recommended practice. And because this is a examination at a medium level for API examination, so you should know the basics. So most of the question would be basics about the meaning, the vocabulary would play an important part here, and the concept and the knowledge. So these are the basics that API wants to verify that you understood this. And look at the table of contents, see how they are structured in the codes and recommended practice. This is often overlooked because then you have difficulty during open book and go search for them, because you should know how they are structured, so you know where to look for. The closed book part of the exam question comes from codes and recommended practice, the ones that inspectors expected to know on a daily basis and using it on a routine basis. So you should be able to answer this question from top of your head without referring to codes and recommended practice. These are called practical type of question or awareness type of question. Don't worry, we shall supply you with enough presentation, more question, lots of flashcards and pictorial, and so you don't forget them during the exam. On 50% of question, as we said in last module, comes from 510, 572. So these are the two most important documents that you have to study. And also please remember the difference between them. The API 510 code is an inspection code. It's mandatory. It tells you what to do, what not to do, what is allowed, what is not allowed. While the 572, like any other recommended practice, this is good engineering practice. Okay, so it tells you how to do it, when to do it. So as an inspector, you would be using this 572 on a daily basis. Because that is like a guideline for you. So most of the closed book comes from 510 and recommended practices, because this information is supposed to be used by inspector on a daily basis. For open book questions that refer to table, graphs, you shall have access to both of these codes, ASME codes and API code 510, and also the recommended practices. So the reference material, to sum it up, are as per publication effectivity sheet and the body of knowledge 510, with the important section being on 671, 7274, which is mentioned in body of knowledge. So anything mentioned in body of knowledge, you should study it doubly, because that is what the API says that they expect the inspector to know. Okay, and then the damage mechanism, there are around 15-16 damage mechanisms you should know, and also the vocabulary, terms, definitions. Then you should know about inspection of pressure vessels, pressure relieving devices, just the very basic. What is a safety valve, what is a relief valve, how they are tested, what sort of damages or corrosion you might expect from them, that sort of thing. And then welding inspection and metallurgy, that should be read in conjunction with ASME section 9, because section 9 is about how to write a WPS and PQR and welding performance qualification, WPQ, whereas the 577 is about the welding inspection you do before, after, and during the welding processes, the damages they might encounter. 578, the material verification program, as famously known as positive material identification. You should know the very basics, the types of tests that's being done, and the program. So the difference between PMI and MVPs, PMI or positive material identification is part of the program, and the program concerns the procedure, what to do in case of non-conformity, how addresses other issues such as reporting, training, recording, and etc. ASME section 5 is the code that is used for writing a NDE procedure, and you need to know about the articles 1 general, RT, article 2, article 6 and 7 MTPT, and then just UT with a 0-degree probe for lamination check and thickness measurement only. Okay. On ASME section 8, construction code, you should know about UG general requirements, UW welding, UCS carbon steel, and appendices 1 to 4, 6, 8, and 12. And important parts are here: UW3 about joint category, UW 11, 12, 16, 20, 27, and we will go about and explain what each one means. So you should remember these clauses in ASME section 8. I remember that most of the API, although it supersedes ASME section 8 during the operation and maintenance, but it's actually taken from ASME section 8 and frequently refers to that. And the last one is ASME PCC2, which is the guideline for repair of pressure equipment and piping. So within the next 8 modules, we shall cover all these, complete with flashcard, practice questions, quizzes, and highlight portions of the actual documents. So let's first pick up what is a code and what is a recommended practice. So as you know, code is a mandatory, cannot be violated, otherwise you're having trouble certifying the vessel to the jurisdictional requirements or according to the law, if API 510 is applicable or ASME section 8 is applicable. Now, recommended practice is actually just a combination of experience and good engineering practices, good fabrication practices, and is a recommendation. So if you deviate from this, it's just advisory. It's not violating the code if you do that. So you're allowed to, if you have a sound engineering reason, you can always deviate from the recommended practice. So normally codes are all based on scientific conclusions, and that's why the recommended practice are mostly practically oriented. So that's why you see that there is a lot of empirical formulas, trends, graphs, and to show you how the overall the picture and how to handle different situations. So the analogy would be like a WPS, building procedure specification, and building instruction. So the builder does not need to know about all the essential, non-essential parameters or the PQR and its associated with both. So all the builders need to know is the range of amperage and voltage, the building speed, type, size of electrode, building position, number of passes, and if any preheat required. So as long as he knows this and how to apply them, that's good enough. So for example, in recommended practice, always say if you want to preheat, do 4-inch or 4T, T being the thickness of the component from each subject valve, whichever is more. It's not coming to very scientific calculation telling you why that is the case. I just tell you that's it, and you use that from, like take it as a face value. You do not really need for practice to have very complicated formula to come to the right number and all that. So in my opinion, the codes are mostly engineering based, while RPs are experience based. Okay, let's go to document navigation during open book examination. So before going to the relevant section, as I said, you need to know which document you need to look at in order to find a particular topic. So you should know roughly where you can find that piece of information to solve an open book question. On top of that, you need to know which section you need to go. Some of the codes are big, they are 1,000 pages, and so it is quite time consuming if you don't practice and you don't go to the right section of that code and look for the information that you need or the formula you need to do the calculation. And overall, the first advice I would give is that do a lot of practice. So get to understand the structure of the code, how the code is actually sectioned and edited, and then do a lot of practice. So that makes your life a lot easier during open book question. And secondly, if you cannot find the particular thing and it's taking a lot of time to find the right information, the relevant information, then you can look at the table of contents to see which section you should go. If that doesn't help you, then you can go to the list of tables. Each of these codes, and they always have a list of tables. So from the tables, you might, the number of tables are not as much as the table of contents, so it's much more concise, or list of figures. So from there you can quickly find out which section actually you should go, and then zoom in. Okay, so these are the two advice we always give. One is the practice, and secondly, find the structure of the code obviously beforehand, and secondly, to go to list of tables. If not, go to list of figures and list table of contents, and then that would be quick. If you see that still you can't find them, just make a note of the number of the question number and jump to the next question. You just don't have too much time to waste on that. So there might be a lot of other questions that are easier to solve, and at the end, if there is enough time, you can always come back to that question and look for it. So sort of you need to manage your time. And then the other thing is you always need to do read the PDF document. And obviously nowadays nobody got a hard copy anyway, but you can highlight the PDF document, and your eyes get used to it, which page you can go for Azimuth section 9 to determine like the qualification range, say for a pipe diameter, thickness, or etc. So it's all about practice, flagging off, tabbing, highlighting, and so you get the hack of it. It's something that you need to learn how to use the codes and where to look for. The other set is API 510, 572, 71, 77, 76. These API documents, they are a lot smaller than ASME codes. They're easier to go around, but and you can get the find the information a lot easier. Okay. In the following modules, we'll talk about all the important topics and tables, and this should help you to get an idea where to look for. Unfortunately, the list is not exhaustive. Vocabulary. There's certain definitions that you need to really get the concept and meaning of them, and that we are highlighting it here so you can understand, and they should be treated as potential exam question. Now, order of precedence. If there is a contradiction, say between API 510 and ASME Section 8, and as we know, API 510 is applicable the minute the vessel is put into service, the first fluid is gone into it. So if there is any contradiction whatsoever, then API 510 take precedence. Okay. Normally, the codes always take precedence of recommended practices. So if there is say for example a contradiction between 510 and 572, so obviously 510 is a code mandatory, so it takes precedence. So that is called order of precedence. You have to see that if there is any contradiction, then you should always follow the one which has got a higher authority, in this case codes. Okay. So let's see what's the difference between a repair and alteration. This could be a potential exam question. Repair basically means repairing something, and there can be minor repair, major repair, and to restore it to the vessel to its original condition. Okay, so to restore, that means repair. Now alteration means that repairing the vessel, but then the integrity operating window or the original, say for example operating pressure, temperature has changes, like you can increase the pressure because you have reinforced the vessel, and or the other way around. So you have re-rated the vessel. It's called re-rating. Now if you demote the vessel, like for example you got a minimum design thickness that you need to maintain the pressure, but then the alternative, the corrosion allowance you don't have enough corrosion allowance left until your next inspection interval, and then you cannot repair it, then you take off some of the thickness reserved for the design pressure, but then you have to bring down the working pressure so that there's not that much thickness that was originally intended for is needed. So use that thickness. Part of that thickness was reserved for design by bringing the pressure down, and use it for corrosion allowance, and if you know the corrosion rate. So that's called derating. So in a nutshell, any repair, such as replacement of parts with same or similar parts, like for like, or restoration board, called the repair. And as long as the integrity operating window, such as say maximum allowable working pressure or minimum design metal temperature, does not change. Whereas alteration means that if you change any integrity operating window, such as MAWP, MDMT, etc., or the fluid. So repair needs approval of the inspector only, while alteration, because there is a design change here, it needs the approval of both the inspector and engineer. Now repair examples are, say, like for like or duplicate, replacement, addition of any reinforced nozzles less than or equal to the size of existing nozzles, and or any nozzle that does not need reinforcement, or any welding, cutting, grinding, or pressure containing components that does not change integrity operating windows such as MDMT or maximum allowable working pressure. Now, alteration examples are any restorative work that results in a change in IOW or MAWP. Okay, we talk about re-rating, that is a result of alteration, and we talk about derating, which is demoting the vessel. Okay, for example, if you increase the pressure, you're upgrading the vessel. Okay, but if you decrease the pressure, you're downgrading the vessel. But the temperature works the other way around. So if a decrease, not an increase in minimum design metal temperature, is actually an upgrade, unlike maximum allowable working pressure. Because in this sense, for example, if you have a vessel that is working as 10 degree Fahrenheit, is superior than a vessel working at 20 degree Fahrenheit, because it can cover a longer range. It can even work under colder pressure because the metal turns brittle as the temperature goes down. So if it can work as a lower temperature, then it's got a, you are actually upgrading here. So alteration also normally requires a pressure test unless exempted in writing by both the engineer and inspector, while the repair does not normally need a pressure test unless, again, recommended or deemed reasonable to do by the inspector. Okay. Now, what is examination? Now, examination, they say, okay, it's QC activity. Some people, they call it NDE, some people call it NDT. Now, the term NDE is non-destructive examination is actually taking prominence rather than NDT, non-destructive testing, because testing is reserved for mechanical testing, pressure test, tensile test, hardness test, that sort of thing. Whereas NDE examination is trying to find the get some information from the material without actually destroying the material. So NDE never destroys the material or damages the material, and hence NDE, they call it examination. Now, the analogy would be the NDT technician normally has a procedure. He works according to procedure, and if he's allowed, he evaluates the indication or discontinuity and see first it's relevant or not, and then size it. So find out the type of discontinuity, the location of it, and when you do the interpretation, if it's allowed by NDT examiner to do that, he compared that discontinuity that he discovered based on the size, type, and location, and check it against acceptance criteria, and would note in the report whether that is acceptable or rejected. So if it's rejected, then it needs to be removed, and then that part needs to be repaired, or the whole thing needs to be discarded, depending how they decide to go about this. So if we want to give an analogy, it's like you go to a doctor, the doctor gives you some, in order to give you some prescription, he might refer you to a lab to do some blood tests, some radiography, some ultrasound, CT scan, something. And then once the result comes in, then he prescribes you the medicine or the further course of action for recovery. So ND is like the lab, and the doctor is like an inspector. Okay, so although the doctor doesn't know how to do the test, but eventually it's a doctor who would decide what course of action to take, and actually, so same way the inspector actually is responsible for interpretation, or he can let the examiner do it, but eventually it's the inspector who would need to eventually approve the NDE examination. So this is very important for you to understand that the NDT examiner can only do the interpretation as well, if authorized by inspector. In any event, it's the inspector who approves the examination report, and the inspector is the final authority for accepting, rejecting the QC and ADT examination points. Okay. Now, if you go to body of knowledge, this is what API says an API inspector is expected to know, and that's what you are going to be tested against. So you should be able to do thickness measurement, inspection interval, and you should know about the vessel integrity, right? Some units, remember, are in SI units, and some of them are US customary units, inches, feet, PSI, etc. So you should be able to use both systems. And you should be able to determine the corrosion rates and the inspection interval, the metal loss, and they have referred to these sections, BPI 510, 74, 71, and 72, and remaining service life and remaining corrosion allowance. Very simple calculation, and then finally you find the inspection interval. So based on the corrosion rate, so that's normally say 1 tau per year. You can see that up to how much corrosion allowance is left, and depending on the corrosion rate, you can do a simple division and then find out the life of the vessel. And normally they use a half-life rule, so divided by 2, you find the next inspection interval. And these are mostly this calculation of closed book. So you should know about the joint efficiency, which is directly related to amount of NDT done. And for that, API refers you to ASME section 8, UW3. It is a very important figure there. And you should know what are category A, B, C, D, mostly A and B. A being longitudinal belt and B being circumferential belt. And longitudinal belt, because they are going almost twice of the stress of the circumferential belt because of the hoop stress that you can see also from the formula that is calculating the thickness for a certain pressure, that the thickness would be twice for longitudinal belt because they are experiencing twice the load under the same pressure. So that would be the deciding factor. And then you should know about the type of radiography, full spot, so RT1, RT2, etc. The joint efficiency, UW12. So that's directly related to RT, to the percentage of radiography, if it's full spot or none. And the various subcategories of UW12. You should know about the static head, and based on the water with a specific gravity of 1 for each foot, you have 0.433 psi increase in pressure. So if the pressure at the top of the vessel, for example, is X, then, and the height of the vessel is say 10, then you shall have 10 into 0.433 extra pressure because of the static head at the bottom of the vessel. So the total pressure would be the static head plus maximum allowable working pressure at the top. So you should be able to do this simple calculation. Internal pressure, you need to always refer to UG27. These are in the exam we have always brought this mock exam question. We let you see how that is done. Then for ellipsoidal and hemispherical heads, you need to go to UG32, and the external pressure is UG28, but there will be no calculation for that. Some very rare vessels, they are actually not having internal pressure, but it's just say under the water, and the pressure is applying from outside. And you should know about pressure testing, which is UG99 and 100. The gauges, the range of the gauge, the pressure, how the pressure tests need to be done, and the leak test, etc. And then you should go to UG84 for any leak testing. Okay. And especially UCS, the general requirement for carbon steel 66 is very important for Sharpie test, because you need to find out whether you have to do this graph, and the associated tables would show you that whether a particular material from a P number and thickness and the operating temperature, whether it needs a impact test or not. And there will be definitely some calculation coming. Don't worry, we will go through this during the mock exam and during section allocated to ASME section 5, this following modules. You should know about the weld size, and you should be able to do this simple calculation of finding the leg of a throat fillet weld, knowing the throat dimension, which is multiplied by 0.7 or vice versa divided by, and determine the size of weld from UW 16. And you should know about nozzle enforcement. There are so many areas, flange calculation, but there are not many questions coming from this. You just should know the very, very basics. Okay, yeah, we'll go through this. Okay. Right. Then you should know about the welding procedure and qualification evaluation based, which is you should know about the WPS, PQR, WPQ, welder performance qualification, which is coming from ASME section 9, and about the procedures you should know, the welding processes you should know. ICE only would consider shielded metal arc welding, gas tungsten, gas metal arc welding, or submerged arc welding. So it would be a very simple WPS, and you should know the very basics of what WPS constitute, what is a PQR, what is a WPQ, etc. And you should know about the P numbers. So ASME section 8 division 1 is the one that you should refer to during the exam, and there you should know about the joints, restriction on joints, allowable reinforcement, heat treatment, etc. And most of them also is included in the API 510. Non-destructive examination, general requirements, calibration. So there is a definition of inspection and examination we just explained, record keeping requirements, and then Article 2, radiography. Again, you should know about the reports, records, location markers, number of IQIs. They might ask you which IQIs which you need to go to ASME section 5 if it's an open book question. Find the IQI number. We'll have ample practice question on this. And then you should know about liquid penetrant. Article 6, again, you should know about procedures, techniques, examination, records, etc. And Article 7, magnetic particle. And it would be same: interpretation, examination, calibration, techniques, documentation and record keeping, and procedures. And then the simple thickness measurement, which is by UT, which is Article 23. This is probably a couple of pages of documents at all. So you should know the overall how that works. You should also know about some practical knowledge, general practical knowledge and specific practical knowledge. So general, as an API inspector, we bring lots of examples so you get the hack of it, and specific about which lots of question coming, at least 20 question coming from here, is the organization, certification requirements, types of inspection, corrosion and deterioration, welding of pressure vessel material, and these are all sort of practical questions that either coming from codes, recommended practices, estimated remaining life, safety practices, reports, records, rating, and in the following modules we'll talk about them. And then a specific one about API 510, and then the damage mechanism, okay, and inspection of pressure vessels, So as you can see here, the entire document is subject to testing for these 576, 7, 8, and PCC2. Only these articles are used that you should know and we have covered in our course. Okay, and the 3 types of inspection: external, which is maximum interval 5 years, and on-stream inspection, that is using an NDE techniques, and the difference is in external inspection normally you only do the visual, whereas on-stream you do the NDE examination also. The external is mostly aimed at detecting environmental corrosion, while on-stream is aimed at substituting internal inspection in lieu of on-stream inspection, and where it's possible to get the same amount of information in order to determine the inspection interval and the corrosion rate. So it could, under certain circumstances, it could replace internal inspection on stream. Okay. For internal inspection, the maximum interval is 10 years. Now let's look at some terms: accuracy versus precision. Now, accuracy is normally used for calibration. How accurate is your measurements? And precision means variation. So how close are a bunch of thickness against measurements? As you can see on this figure, the first figure, you got a lot of precision. You don't have much variance here, but it's not accurate here. Now, on second figure here, you see the readings are all over the places, but they are almost close enough actually. So there is not much. There is a variance, but they are almost around the, the readings that you expect it to be. So here it's accurate, but you don't have precision. And here it's all over the place. It's neither accurate nor precise. And when everything is together, there is not much variance. And so it's not only accurate, but also precise. Normally the point of measurement on a conditioning monitoring location, or CML, is a diameter of 3-inch maximum, a circular area, and you can take several measurements. Let's see the key players according to the API. So the most important player is the owner user, and the API does not differentiate between owner and user. The reason is that the vessel might legally belong to somebody else, but being operated by another entity. So if things go wrong, the user can always say, oh, it doesn't belong to me, it belongs to owner. And the owner can say, oh, I gave it for that guy to use the other entity, so he should have done due diligence. So in the eyes of API, both owner and user are equally responsible if they are 2 different legal entities. Okay, so they are responsible for operation, maintenance, repair, and code compliance, everything. But the owner might have employ or subcontract an API inspector or an inspection agency who reports to the owner. Inspector will mean API 510 authorized pressure vessel inspector, who is responsible to the owner for inspection and approval of the vessel for continuous safe operation. So the inspector will certify that it's safe. So the inspector is responsible to the owner, but the ultimate responsibility lies with the owner. The inspector can be an individual, or working for an inspection agency, or an insurance company, or for government, or directly being employed by the owner. But it should be an authorized pressure vessel certified inspector. NDE examiner is responsible for performing NDT activities, as we know, and if authorized by inspector, only if authorized by inspector, can prepare the acceptance and rejection part of the report. Okay, so eventually inspector is the final authority in accepting or rejecting, because it's the inspector who is certifying the vessel is safe for continued use. Okay, certification of NDT examiner, this might be a potential question, shall be maintained by his or her employer and shall be available for inspector's review. Now, the engineer, if you look at the term, is a person who is, or a group of person. So it can be a team or just one individual. And by the term engineer, that means pressure vessel engineer here. And it is appointed by the owner user who has enough knowledge in the design, review, analysis, and evaluation of pressure vessel. Why the API says appointed by the owner? Because if the API dictates some terms of what the engineer should be, the owner user could always say, yeah, we got the guy who you told us to get, and now, you know, he made a mess of it, so you are involved. So that's why API doesn't want to get involved with this. Said it's the responsibility of the owner to get a qualified person as an engineer. Okay. Remember that both the engineer and inspector shall approve the re-rating, derating, and alteration. Our repairs do not normally need engineer's approval because there is no change in the integrity operating window. But unless the inspector wants to consult with the engineer on some major repair. Corrosion specialist again should be approved by owner. It actually is representing the owner itself. An individual who is knowledgeable in materials, metallurgy, damage mechanism, and corrosion monitoring techniques. And again, approved by the owner. So integrity operating window is the range that this the vessel can work. It's like you buy a car and it says it can, you know, go so much speed and, you know, that sort of thing. So there is a range here that when you buy a car, it operates the same way a vessel should operate within a certain. It's designed for that range. It's the design input and output is based on that range. It's actually the design output. So some of them are the type of fluid that can be used in the vessel. The speed of the fluid can be one of the parameters. The maximum allowable working pressure can be one. The minimum design metal temperature can be one. So these are all called integrity operating window. Management of change is when you have certain parameters or certain way of working and you change it. Now, when you change the operation or the maintenance or the during the design or the fabrication or repair, you should see how this change affects other disciplines or other parameters. And for that reason, you have to document it. Okay, so it's very important that management of change should be documented, and all the affected disciplines, they should be aware of these changes. Okay. Conditioning, monitoring, location. Normally, you know, you do some measurement and then from some points, and in order to compare it in the next inspection interval, so you mark them either on a drawing as built or on the vessel itself, or somehow you trace it so that you do the same measurement from the same points, so you can compare them. I mean, if you do from different points, you have no references. Okay. So, and this location that normally selected by the inspector and should be all API wants that they should be representative of corrosion behavior of vessel. So always go for the select the places that first it should be accessible, and secondly it should be the where you expect the maximum corrosion. Okay, the weakest link of the chain. So the inspector selects the monitoring locations. QA and QC, QA quality assurance actually plans the verification points, and QC or quality control actually implements them. Okay, so that's the difference between them. One designs the system, the quality system, and the other one actually implementing them. Now, risk-based inspection, obviously, you know, if there is a vessel one-off, if there is a there's a lot of risk involved, and by risk we mean the probability of failure multiplied by the consequence of failure. So there might be the probability of failure might be very high, but the consequence is low. Like some utility pipes might be dripping or, you know, leaking. It's not really that important. So the overall risk is low. On the other hand, the probability of failure might be high, but the probability of failure might be low, but the consequence is very high. for example, there is a one-off vessel that can shut down the whole plant, but then the probability is very low. It's like flying with an airplane, and the airplane, the jet engine fails, and so it is a catastrophe here. But then the probability of all the engines fail is very low. So as you can see, the risk is much lower than driving a car. So you don't have many fatalities in the flying industry than in the road. If you use a road, a lot of people unfortunately get killed on the road, and not many you'll see that any flight disaster. So the probability is low, but the consequence can be horrendous. Now, if a car breaks down, it might not be much of consequence, in terms of fatality, but so that's how it is. So it's a product of probability of and consequence of failure, and obviously inspection efforts can be directed towards more critical parts, locations, and equipment, and they were reducing the probability of failure, downtime, and inspection. Mostly inspection is concerned with the probability of failure. It addresses those areas, whereas the process engineer normally looks at the consequence of failure, and the combination of two would constitute the risk. So this is a formula. Risk is equal to probability of failure multiplied by consequence of failure. Quality assurance manual is a quality management system, and it includes org chart, procedures, reports, recourse, plan. If there was any RBI assessment, determining inspection interval, auditing to see that everybody is working according to procedure, there is no non-conformity. Documentation such as drawings, calculations, any repair rating, recourse, any management of changes that has been documented, any evidence to show that they are compliant with the codes and the specification, and the recourse of qualified builders and qualified technicians and approved WPSs, building procedures, because of training, material traceability, and material certificate. So this is more or less a list of ISO 9000 bound. And temporary embrittlement is reduction in toughness under high temperatures, 650 to 1100, and the most susceptible material is 2.25 chrome 1 mol molybdenum low alloy steel that shows a sudden drop in toughness and fails. You should remember that the embrittlement or brittlement is reverse of ductility, and toughness is resistance of material to deform under the force or stress. And toughness is in numbers or quantitatively is the area under the stress strain curve, and it depends on the amount of stress it can tolerate and its amount of elongation practically. And it's determined by the Charpy impact test, the toughness of a material. And hardness is a resistance of material against penetration or indentation. We will cover them in our next module. That's end of module 2. Thank you.